So this is the reciprocity theorem. And what this one says is that if you have a circuit of this sort, right? And here we can see clearly that we have a voltage source here and we have an ammeter here, right? So that's why the current is coming in and the ammeter is measuring the current through it. What it says is that these two, clearly we can see that these two are in different branches. We have one here and then we have the other here. What it says is that when you interchange them and keep, when you reciprocate them, right? So you move the ammeter to the other branch and you move the voltage source to the other branch, the circuit remains the same, meaning that the voltage that the current as a result of this voltage here, this voltage source here will still be the same here, right? The ammeter will still measure the same what do you call it, current in this branch, irrespective of the fact that you've interchanged them, right? The same thing here. So what we have here is what we call ideal voltage source. So they say ideal voltage source, ideal ammeter, ideal voltage ammeter, ideal voltage source. What this means is that these have no resistances, right? So ideal, so it doesn't take a current from the circuit, right? So then again, that's it for the reciprocity. But then there's the next one. So what we've been saying so far is in applied electricity, the basic equation V is equal to IR, right? So this one is the first side here. The one is saying that when you have when you have a voltage source like this one in one branch of a circuit, and you have an ideal voltage source in one branch, and you have an ammeter in the other branch, and you reciprocate them, right? It still remains the same. The ammeter still measures the same current, right? And this one too is saying that number two is saying that if you have what do you call it, an ideal voltmeter, right? I mean, it doesn't take current from the circuit, right? In one branch here, and then you have a current source in another branch. When you interchange them, the circuit still remains the same. That's why we have this equal to here. Mean that so far as you interchange them and they are on the branches that the other one was on, the circuit remains the same. Nothing has changed, right? So it might look very simple, but it helps you to analyze a lot of circuit, making it simpler. That way, the analysis of the circuit is easier. So let's see. We're going to look at an example here. So this is an example, right? And then the question is like we should find the what's the name? The voltage. The voltage. To find the current, right? Across this 3 ohms here, this 3 ohms resistor. So clearly we can see that since we have two voltage sources here, right? And then per superposition, we can split it. We have a 45 here, we close circuit this side, short circuit this side, right? We have the 35 here, we short circuit this side, right? We've just allocated the current to just see the direction, that's all. Nothing different. But then we are going to do this. Okay, so clearly we can see that this superposition, we split the circuit. We have the 45 volts here, right? And we short circuit the other voltage source, right? We have the 35 here, we short circuit the 42, right? So that's what's happening. In the superposition, it's very clear that if you're able to find the current in this one, what is it? If you're able to find this I2 here, right? That's if the actual thing is to be able to find the current in the 2 ohms here. If you're able to find this I2 here, right, and you're able to find this I1, IE here, when you add them up, it gives you, so this plus this should give you this actual current here, right? So that's this for this proposition, right? But then the reciprocity comes in and sees something very unique. It's like you are doing some kind of like simple algebra or something, right? So let's see. The reciprocity is saying that this same circuit here, right? Let's go over it. So what happens is that this 35 volts here provides you with a current, right? And that current, which is the 1D here, right, is what passes through this 12 ohms here. So he's saying that if you are able, because our aim is to do what? Find the current in this 3 ohms here, right? Okay. So this 35 here provides a current and it gets to the 12. But if you're able to turn it upside down, because let's say you put an ammeter here and then measure the current, right? An ammeter. So let's say you place an ammeter here. That will help you to measure the 1D, right? So if you're able to measure the current there, right, and now you move this 35 volts to this side, right, and you move this ammeter to this side, the 1D current here will still be the same thing here, right? And by doing that, you're able to get the current that passes through the 3 ohms due to 35 volts. Right? 5 volts is giving a current 1D here through this 3 ohms. You can do a proportion, right? And we see like if 35 volts is giving us about, let's see, a 1D something, right? So we can see that this. So you see the arrangement. Let's go over it one more time. So right, so let's clean this. Okay. So looking at this one, you can see that the arrangement is actually the same. So we have a 12 amperes, sorry, 12 ohms, 6, 6, 3, 3. So the arrangement is the same. The only thing here is that we have a 35 here and we have 42 here. They are providing currents in the same direction, right? So you can see that if the 35 is giving you about, let's say, 1 amperes, 1D ID amperes here, then the 45 will give you about more. 45 volt to give you more. So like you do a proportion, is if more or less divide on the 42 rather. Right. So 42 on 35, and then multiply by the value for the 1D, and it gives you the current that is 42 here, right? This, so to basically, after you found this 1D here, this will help you to find the, what's the name, the 1A here, right? So after that, you're able to add the 1D and then 1A, and you're able to say, oh, the current passing through the 3 ohm resistor is that. So that's how it is done. Right. Okay. So now let's see. We're going to go through the procedure one by one and see what we get. Okay. So now we have the understanding. We're just going to go through it, just the calculations. We get a theory of the now that how useful the reciprocity theorem can become. And now here we are, in this case, we are combining two theorems, the reciprocity, superposition, to help us find what we are asked to find, which is the current in the 3 ohms resistor. Okay, let's see. Okay. So first of all, we split it, and then so looking at it, we want what is actually passing through the 3, right? So we know that 3 is right. We know that 3 is here, right? And then this one is having the 3 here, right? So it's easier to, let's say, whichever way you want, you can shift, do any one of them first. So we could have chosen to keep the 3 as well constant here, but remove the 42 and bring the 42 here, right? So we have the same segment. But that's what we've chosen now. So let's do it this way. So basically, you know the procedures you have to go through. So first of all, we should be able to find this I2 here, which is this I2. Okay. So now the first thing we are going to do is to find the current. This okay, we swap it, right? This ID is what we are trying to find. So the first thing we're going to do is to find this ID here, this one. And this how. Okay. So before we are able to find the ID, we should be able to find the main current from the circuit, right? So where is it? So our aim is to find this ID, and then with that we find this, right? And then with that we are able to find the amount that this 42 here is contributing to this theory, which is the IE, and we add them up, we've gone over this already. So that's what we do. A minute. Okay, so look, so now we are not working with this, we are not working with this, we're working with the one on cancel. So right, the loop that we are considering right now, so what we need right now is to find the current, right, which is this ID. But this ID is actually coming from this I2 here, right? It's coming from this I2. So what do? It's actually a current division. This I2 gets to this junction, this node here, right, and it splits to this IC and ID. So we need to find I2. And I2 from the look of things is the current from the only voltage source, which is this 32 here, right? So V is equal to IR. Then what do we need? We need to find, we have our V to be this, we need to find our R, then we can find our I, right? So how do we find our R? Looking at this very well, this is not Thevenin, right? We are not doing Thevenin, so we just see this two here, this two elements here to be in parallel, right? So basically we have the total R, right? So here instead of RT, you just write RT. The total R is 12 parallel to 6. Let's try this one. 12 parallel to 6, right? Put it in bracket. And what we have again, when we do this to be in parallel, to be in series with a 3, right? So plus 3. And this is how we punch it. Put that to a sum because there are 2. Right? Plus 3. And that gives us what? 7 ohms, right? So now that we have this, we can we'll be able to find the main current, which is the I2. So we go on and see this I2 here is equal to V on R. We have our V to be 35, and we have our R to be 7, and that gives us 5, right? So 35 on 7. Yes, so that gives us 5 amperes, right? But we know that this two what do you call it, I2 here is what splitting to give us the ID, right? So basically we're able to find an ID using current division. So ID, now we've explained all the concepts, so now we are just going straight for the calculation, right? So ID is a part of I2, right? So current division. So if it's current division, when it gets here, it's split between the 12 ohms and the 6 ohms, right? So we are trying to find for the ID, which is for the 12. So we put a 6 here, and we get 6 plus 2, right? Times the actual current. So that's 6 all on 6 plus 2, 2, right? Times 5, and that gives us 3.75, right, amperes. Let's write this for 75 amperes. We overlooked something. There's actually 6, right? The current split, now we are looking at this one. The current split between the 6 and 12, not 2, right? So 12 here. So that gives us 6 on 6 plus 12 times the 5, right? That gives us 5 on 3, right? So 5 on 3, rather. That's about 1.6. So 5 on 3 amperes. Okay. 3 amperes, right? So that's for ID. Now we have ID. When we put it in this circuit here, so now we are done with this one. Let's see this one. So and we work on the one below. Okay. So it's clear that this ID here, the current passing through this 3 ohms here. So let's make it clear. This is the reciprocity. What we are doing this now. So from this to this. So from this to this is reciprocity, right? Okay. So then means that the current that we have here, let's write it. The ID that we have here is 5 on 3 amperes, right? So we have that. So now we are done with this. So now we are going to deal with 2 to make our work easier, right? So we know that the current passing through the 3 ohms resistor, right? So the current, so let's write that one out. Current through the 3 ohm resistor. So looking at this one, so this is the original circuit. We split it using superposition to get this and this, right? So the current passing through the 3 ohm resistor is basically this. What's the name? Basically this right here, the ID plus the IE, right? So that's ID plus IA. So we have ID. We have ID, yes. And now we are seeing per proportion. Since this 35 here, right, is giving us this 5.3 amperes here. See the same configuration. We have 12 ohms here, 12 ohms, right? 6 ohms, 6 ohms, 3 ohms, 3 ohms. So if this one is giving us a particular amperes, we should be able to find what the 42 is giving us. That's basically like doing some proportions, right? So 42 amperes. So the current provided by that 42 volts, right? So let's see the portion of it that is passing through this 3 ohms here, which is the IE. That's what we're looking for right now. So this is what we do. We just said that I'm going to write that. So if I 3 ohms is giving us 5 on 3 amperes, then the I 35 volts rather. If 35 volts is giving us that, 35 volts. If 35 volts is giving us that, then the 42, right? 42 volt, this is what it will give us. Will be, so we have 42 on 35 times the 5 on 3 amperes, right? Here's volt, but they cancel out. Right? So this was giving us, we have 42, 35 times 5 on 3, and that gives us what? 2 amp. Okay, so this is the 42, right? 42. So that's this, right? IA. So our IA is this 2 amperes. So we are saying that the current passing through the 3 ohms in all. So right, this is the original circuit, but I've split it into this and this. We are saying that in order to find the current passing through the 3 ohm here, this is the one from this side, it's I2, right? So we add this I2 here, right? I2. And this one too is passing through the 3 ohms, right? So we have what? IA. So this two are what we're adding to get the current passing through the 3 ohm resistor. So IA, I2, right? And then, so the current to the 3 ohm. This namings of current depends on you. Just name it in a way that you'll be able to identify them easily. So IA plus ID, right? ID. Okay. So now we are going to the diagram. So IA. Okay. Okay, IA. So looking at it very well, IA moves in this direction, right? Moves in this direction. So, and we have that IA to be. So from this, we have to choose a conversion, right? So let's see. You can choose anyone, but the direction will just tell whether it's positive or negative. The other way around. So let's say we choose to make a keep what's the name? To keep this to be a positive, right? So IA is what? IA is 2 amperes, so that's 2, right? So if IA is positive, ID will where's ID? Oh, it's actually I2. This I2. ID, yes, and I2. So this should be I2. I2. So we're adding this 2, right? IA is 2, and then I2 is I2. Oh, I2 was it? I2 is 5 amperes, right? So this should be in the opposite direction, 5 amperes. So this gives us, we have negative 3 amperes. So what this is saying is that if we are choosing this, so you see when we said that the computation set this direction, right? So this means that the actual direction, the current through the 3 ohm resistor is in the opposite direction that we've chosen. So we chose this, but then we do the computation, we get negative. So meaning that the actual direction of the current through the 3 ohm resistor is this. Okay. So that's it. Using the superposition and then reciprocity, which is the main thing we are doing here, to find the current in the 3 ohm resistor.